What's up, mathletes? This is section 2.2, day number 2 of solving absolute value equations and inequalities. Yes, last video was the equations, and today we're going to look at the inequalities. Look at this. We've got the absolute value of x is less than or equal to 3, so it has both absolute values and inequalities in it. One of the core concepts we got to think about is that they come in two varieties, two flavors, like ice cream, just chocolate and vanilla, and you got to figure out, is it case 1 or is it case 2? And so here, case 1 kind of looks like this, and you can see case 2 looks like this. The only difference between the two is that the inequality is flipped. So you just have to, deciding between case 1 and case 2 is a question of, is it pointing like this or is it pointing like this? And case 1 would also be like, even if there was no line underneath here, if it was absolute value of x is just simply less than 3, not less than or equal to 3, then it would also be case 1. All right, so let's just look at these cases individually and see how they play out. If you want to just guess and check some of the actual numbers plugging in here, which are the solutions? Well, 0 works. You put 0 in, the absolute value of 0 is less than or equal to 3. Positive 1 works. Positive 1, the absolute value of 1 is still less than or equal to 3. 2 works. 3 works here. And even negative 1, negative 2, and negative 3, you take the absolute value of negative 3, and it's actually positive 3. And then positive 3 is less than or equal to 3. So I've circled in green all of these numbers because they all are solutions to this absolute value inequality. And if you wanted to actually do a number line, and you could put a closed dot at negative 3 and a closed dot at positive 3 and shade everything in between those two dots. So it would look like this. It would look like closed dot at negative 3, closed dot at negative 3, and then you shade in what's in between. You do the same thing right now with your hands. Go like this. Case 1 looks like this. Dot, 2 closed dots, or sometimes open dots, or like open dot, or open dot, 1, whatever. But the shading in between the two dots, whatever kind of dots they are, in the middle. Case 2 looks a little different. You just flip around the inequality, and all of a sudden, you've got different numbers that are solutions. Negative 3, yes, it still works, but if you take the absolute value of negative 4, that's actually positive 4, and now that, it didn't work before, but now it does here. The absolute value of negative 4 is positive 4, and yes, it is greater than or equal to 3. Same thing with negative 5. Same thing with positive 3, positive 4, positive 5. You take the absolute value of 5, and it is greater than or equal to 3. Solution, yay. But look at this, the ones in the middle are no longer solutions. 0 doesn't work because the absolute value of 0 is still 0, and it's not greater than or equal to 3. And negative 2 doesn't work because absolute value of negative 2 is positive 2, and then positive 2 is still not greater than or equal to 3. So, and if you do a shaded region of the inequality, it would look like on a number line, you would have a closed dot, sometimes open dot, but in this case, closed dot at negative 3, closed dot at positive 3, and you don't shade in the middle, you would actually shade on the outsides. Do that with me right now. This is case 2. Case 1, case 2, shade on the outsides. All right, so that's what we got to know. And the stuff that happened that we learned before about first solve for the absolute value and then remove the absolute values and then continue to solve still applies here. So that was stuff from yesterday. Let's take a look at this. Example 1. You have the absolute value of 4x minus 8, close absolute value, and then minus 5 is less than 11. So first thing you got to do is move this minus 5 to the outside. That's on the outside of the absolute values. Adding 5 to both sides, you get this. Now you got to figure out, is it case 1 or is it case 2? The symbol looks like this, so it's going to be case 1. And it's kind of good to have this as a reference while you're actually doing it, like open up your notes and while you're doing the ALEKS and you're looking at this. So case 1 looks like this. So what we're going to do is we're going to go from something that looks like this down to something that looks like this. Case 1, so we're going to write 6. You can see 16 gets carried here. 4x minus 8 is here. We're removing, this is the process of removing absolute value symbol. And then we're also going to put another symbol here as negative 16. So this algebraic expression is going to be simultaneously greater than this, negative 16, and less than this. It's in between these two numbers. All right, so let's solve for x. and we can add 8 to all three parts, so it becomes this, and then dividing all three parts by 4, you get that. And then so you have, in the end, you have -2 is less than x is less than 6. These are all the numbers that are going to make the original inequality true. And you can see case 1, solid dot, closed dot, and then shading in the middle, in between -2 and 6. Here's the inequality form. Here's it graphed on a number line, and here is it in interval notation. All the numbers between -2 and 6. Oh no, it should be including. These should be open dots. I gotta change that. Okay. Yeah, these should definitely be open dots. So, let me go make a note of that. Okay, let's do the next one. Similar idea here. We've got an absolute value and stuff on the inside of the absolute value and stuff on the outside of the absolute value. So let's undo the stuff on the outside first. Boom. All right. So undoing the stuff on the outside, we first undo the addition with subtraction by subtracting 5 from both sides to get this, and then we multiply both sides by 2 to undo the division, and you get this. Now you have absolute value, symbol, number. And notice, case 1 and case 2 is very important. You have to make sure that, I didn't say this earlier, you have to make sure the absolute values symbols are on the left-hand side. And only then can you make sure that and only then will you know that you're evaluating case 1 or case 2. So if you for some reason have absolute values on the other side, just take a moment to flip the inequality and flip the symbol while you're doing it. Okay, so look at this. You can see this is absolute value symbol greater than or equal to, and then number. And so looking at our handy dandy notes, we can see this is case number 2. If it's case number 2, then the format we do for undoing the symbol looks like this. You go from one statement actually down to 2 statements. Here's the positive version. You can see there's no absolute value, it's just regular x, same symbol here, greater than or equal to, same number here. Here's a negative version. Notice the symbol gets flipped. It was greater than or equal to, now it's less than or equal to. And it was 3, and now it's -3. It was absolute value of x, and now it's just regular x. So we'll do the same thing. So we're taking this, and now we're going to rewrite it as 2 different statements separated by the word or. We've got 6x plus 3 on both of these statements, 6x plus 3, 6x plus 3. This was positive 18. This is the positive version, 18. The negative version has a negative 18. The positive version has the same symbol, greater than or equal to, here. And the negative version has a less than or equal to symbol here. And from here out, we solve them like normal inequalities. You undo the addition on both of them. You undo the multiplication on both of them by dividing by 6. And you get x is less than or equal to -3.5, or x is greater than or equal to 2.5. So here you can see that we've graphed those points, -3.5 and +2.5, and it's not shading in the middle, like case 1. Case 2 looks like this, you're shading the outsides. This shading corresponds to this part right here, and this shading corresponds to this part right here. So there it is. The number, or the value for x, could be either on this one or on this one. Either one is fine. So that's why it's separated by the word or. And in order to note that in interval notation, you can see the left part shading over here it goes from -infinity up to -3.5, includes -3.5, and then U symbol, that's the union. Combine all of these numbers with all of these numbers in the same on the same number line. And so here you got 2.5, or including 2.5, and we're going up to infinity. This might be a great time to talk about my favorite restaurant ever. It was an Italian restaurant in Guatemala. And you might be like, what? Italian restaurant in Guatemala? Well, yeah, you've got Italian restaurants everywhere. This particular one was like in the mountains of Xela, which is not the capital city. You have to take where I lived in the capital city, and you have to take like a bus, 4 hours to get there. And it's in the mountain towns. and it's like, like it's remote, and it's like, what is an Italian restaurant doing in this far off region? Like I had to take a 4 hour bus ride to get there, and um, the food was super authentic. The dude had definitely immigrated from Italy. I like to have this backstory of like he has like, I don't know, got into trouble in Italy and like had to leave and just hide out in Guatemala, and eventually started a restaurant, and and it was just super authentic Italian food in the middle of Central America, and it was just really awesome. So that's where that's your audio check. Italian restaurant. All right. Example number 3. Um, so here we go. We got this going on, and you see there's stuff on the inside of the absolute value, stuff on the outside of the absolute value. We're going to undo the addition first to get this. We're going to undo the multiplication next to get this. And notice when you divide both, anytime you multiply or divide an inequality by a negative number, you have to flip the sign. So in this case, we are dividing both sides by -8 to undo this multiplication. And so it goes from greater than or equal to less than or equal to, and that's flipped. And that's just 3. Looking at this, it fits the pattern of absolute value less than or equal to 3. So it's case 1. It's going to be solid dot, and then shaded right there. Case 1. So we got here -3 is so case 1 looks like this. We're going to take the algebraic expression and put it in here, no longer with absolute values. This is the process of removing the absolute values. This is how you undo the absolute values, and so you no longer need to write them anymore here. And then the positive version 3 is over here, negative version is over here, and we keep the same symbol. So x plus 14 is got to be in between -3 and +3. Undoing the addition here, plus 14, you subtract to get subtract 14 from both sides, and you get this. So we see we've got to have solid dots here between -17 and -11, and there they are. There's the solid dot, and you shade everything in between. Case example number 4. Dang it! Forgot to change these to open dots. These should also be open dots as well, right here. Okay, so did I provide the interval? It didn't provide the interval. It doesn't say to do so, but this would be all the numbers between -17 and -11 in with square brackets in between. Okay, so example number 4. This is 8z plus 20 minus 2 absolute value of 2z plus 4. That's a little interesting, because now we've got z on both sides, and the absolute value is on the right-hand side. All right, well, let's see what happens. We've got here, so one thing I did was actually divide all the terms on both sides by -2. That would be, the reason I did that was because the first step is to undo the stuff on the outside of the absolute value. That's the negative times -2 right here. So undo that with division. And so then we get divide all the terms. Divide all the terms on both sides by -2. 8z divided by -2 is -4z. Positive 20 divided by -2 is -10. So it's -10 right here. Dividing by both sides by a negative number, gotta flip the sign. Used to be greater than, now it's less than. And so we have this right here. And I can't evaluate case 1 or case 2 when the absolute value is on the right-hand side, so I'm going to flip it around so that now it's on the left. Absolute value, it reads, from left to right, it reads absolute value, symbol, everything else. Great. Now I can see that this symbol is case 2. To undo that, that means I have to write 2 statements separated by the word or. The positive version is the exact copy, just without the absolute values over here. And the negative version has this flipped, and then we put a negative symbol outside of everything else here. Like, this is the negative version of all that. And I mean, this is just the process of undoing absolute values. We've got case, so you can see there's an absolute value here, and there's no absolute values here. And this is really the only way to undo absolute values when it comes to, inequalities. You've got to and we have to take special care to undo the absolute values. So we solve these. On the left-hand side, the negative side, we can distribute and get positive 4z plus 10. Subtracting 4z from both sides, we get negative 2z. And then subtracting 4 from both sides, we get negative 2z is less than 6. And then dividing both sides by negative 2 to get z all by itself, we get negative 3 over here. And notice the symbol is flipped because I multiplied or divided by a number that is negative. On the positive side, we get 2z plus 4 is greater than this. And so let's add 4z to both sides. We get that, and then undo the addition by subtracting 4. We get this. Dividing both sides by 6, we get this. So if we were to graph them, they would actually, you notice they're both pointing in the same direction. Z is greater than. Z is greater than. So we're going to shade on the right-hand direction. Both of them. This dot there's one dot at negative 3, and there's another dot at negative 2.3333 repeating. So it's a really weird shading. If you were going to graph both of them, you'd have a solid dot here, maybe even on this. I separated them a little bit so you could see, but they could be both on the number line, one pretty close to each other, and they're both shading in the right direction, up towards positive infinity, which is really bizarre. So like, how do you express the answer? Actually, you could simplify it and combine them both and just say z has got to be greater than, like if z has to be greater than negative 2.3, or z could be greater than negative 3, you can combine those two statements into one and just say that z has just got to be greater than negative 3, because that expresses all of these numbers and all of these numbers in one statement. All right, let's talk about food. Survey found that 58% of American adults eat at a restaurant at least once a week. The margin of error was within 3 percentage points. Mathematically represent the survey's confidence interval below. So, 58%, but we're not exactly 100% sure. Like it could go a little bit higher or actually lower. The actual number, the actual percent could be a little bit away from 58%. By how much away? 3% away. So let's write the knowns that we have is that the survey yielded a number of 58%, but there could be 3% margin of error. If you're going to graph all of the possible, and then the unknown is what the actual percentage is. Like, there's the survey's result, and then there's the actual. If you were to like survey absolutely every American adult, and ask them how many of them eat in a restaurant at least once a week, the actual number could actually be a little bit higher than 58% or actually lower, but we don't know what it is. That's all because there's a margin of error. So what's unknown is the actual percent, and we'll call that x. So the distance in a number line, this is from previous notes, the distance on a number line between two things is like this. Absolute value x, you take absolute value of the two numbers and you subtract them. Sorry, I want to rewind a little bit. If you're going to graph all those, you can see here's 58. You go up 3%, you get 61. You go down 3%, you get 55%. So all of these numbers shaded are within the 3% margin of error. And if you were going to just make an inequality from the graph, it would look like this. If you're going to integrate absolute values, basically you're saying that the distance between the actual percent and the survey percent has got to be less than or equal to 3%. So this is, remember, this is from the last notes, this is distance. The actual percent and the distance between the actual percent and 58 is represented this way. This is distance. And when you subtract the two and take their absolute value, the distance has got to be less than or equal to 3%. This might seem like unnecessary, especially based on we've got a great graph and we've got a very simplified inequality and interval. But there are lots of calculus applications for absolute value inequalities. So my encouragement would be to ask questions about this and try and get as comfortable as you can about this kind of expression. Remember, distance less than or equal to margin of error. Sleep. You can find out how much sleep you need by going to sleep without turning on an alarm. Once your sleep pattern has stabilized, record the amount of time you spend sleeping each night. The amount of time you sleep plus or minus 15 minutes is actual your sleep need. So suppose you sleep 8.5 hours per night. Mathematically represent your sleep needs below. Same idea. 8.5 is in the middle. And, start with knowns and unknowns. What do we know? You know that you actually slept 8.5 hours, and we have a tolerance of 0.25 hours. Like, it could be off by 15 minutes, which is a quarter of an hour, 0.25 hours. So plus or minus, you could be, the data point that we have is 8.5, and you could actually just be off by 15 minutes either way. What is unknown? The unknown is your actual sleep need, which is X. So this is the one data point, and your actual biological sleep need is very close to it, but we don't know exactly what it is. It'll just be X. If you were to graph that, here's your data point, 8.5, and the margin of error, the tolerance, the wiggle room you've got is 15 minutes in either direction. So that's a quarter of an hour. Your actual biological need could be as high as 8.75, or it could be as low as 8.25. If you're going to do that as an inequality, it would look like this, and as an interval, it would look like this. You're going from the X value of 8.25, including it, all the way up to 8.75 inclusive. So turning it into an inequality would look like this. Your actual sleep need is unknown, but the one data point you have is 8.5, and so the distance between these two has got to be less than a quarter of an hour, 15 minutes, or 0.25 hours. We're doing less than or equal to here. Again, it's the same idea, just putting it into absolute value inequalities. Here, the tires. The recommended inflation of a car tire is no more than 35 pounds per square inch. Depending on the weather conditions, the actual reading of the tire pressure could fluctuate up to 3.4 psi. Mathematically represent the interval of tire pressures in all weather conditions. So what do we know? We know that the recommendation is 35 psi, and it might fluctuate 3.4. Let me grab some tea real quick. If you're going to put that on a graph, you can see that the recommendation is in the middle, 3.5, and it fluctuates up and down. 3.4 higher up to here, 3.4 lower down to here. You want to turn that into an inequality, it would look like this in between the two numbers, and the interval would look like this. And so what I'd like you to do is try and figure out what's underneath the red dot, and I hope you do well. I think you can figure it out based on the pattern. This idea of tolerance and a percent error, margin of error, is incredibly important when it comes to engineering. For example, if NASA, if you're just like cutting a piece of wood because you need like you're not even building a house, you're just like trying to cut a piece of wood that you can prop up your table, and you say, okay, I need like a 3 foot long piece of wood, then your margin of error could be quite large. It doesn't really matter. You're just using it to stick underneath, just using it to like prop up a table. It can be very small. A very large margin of error, you could be like 3 foot at 3 inches, or 3 inches less than 3 feet. It doesn't even matter that much. But if you're working for NASA, then margin of error has got to be incredibly small. It costs a lot of money to be incredibly precise. If you're building the next space station or the next shuttle or whatever it is, then you've got to have a very low margin of error, and that costs a lot of money. So engineers are always talking about, okay, I need a 3 foot piece of wood. Do you need that to the nearest millimeter, to the nearest micrometer? Like how precise do you need it to be? So that's your encouragement to show you that this is really important. Thanks for listening. Inspire today. I can't wait to see you in class and talk about what's going on. Maybe you can ask a question, and I'll see you later.